This is Cockatoo for Eureka. You're listening to Muppet, the Gotham Cockatoo. He's excited because he just got a cashew nut. Not handed to him, he actually fished it out of a puzzle box. To get it, he crafted some sort of a spoon out of cardboard with his beak. No shorter or any longer than necessary, and used that to get the nut. Pretty impressive, right? Surely a smart bird.
I agree, that is pretty awesome. Is Muppet a particularly smart cockatoo, or are all cockatoos that clever?
You're already asking the right questions. We try to answer that within today's episode. But first, listen to this. This is Bob, a sea sponge belonging to the class of Demospongiae. He just contracted his osculum in order to avoid a hungry parrotfish. Isn't that equally impressive and smart? Oh, and he doesn't even have a brain, or any neurons for that matter.
Well, I don't know, it can hardly be smart if it doesn't really have a brain, can it? This behavior must be genetically encoded. Would you call that intelligent?
It doesn't seem intuitive, right? But how do we actually tell whether a behavior or an animal is smart? This is what we are looking at today. I'm Benjamin Lang.
And I'm Nicolas Roth, and by the Science of Intelligence Cluster in Berlin, this is Punching Cards, the podcast about all things intelligent.
In 1386, a culprit was hanged in the city of Falaise for a heinous crime. The murderer was accused of eating infants off the streets. While the crime already may seem outrageous, the identity of the suspect is even more. It was a pig.
And actually, putting animals on trials with proper judges, witnesses, and hangmen was surprisingly common throughout the Middle Ages. It seems a considerable amount of accountability and allegedly something like intelligence was attributed to non-human animals already in medieval times.
While historians are divided about the actual reason for those historic animal trials, some suggest authorities back then just really wanted to demonstrate a strict rule of law and order. Others believe the animals' crimes were attributed to the devil's workings. So it's actually not quite certain whether medieval folk actually considered swine smart enough to be criminals.
True. Historically, sentience and intelligence seem to be mostly reserved for humans. René Descartes, one of the most influential thinkers of the 17th century, who is called by many the father of modern philosophy, had quite extreme views on today's topic. He denied that animals had any sort of reason or intelligence. In his view, humans were the only beings that had a soul, which can make us feel pain, or actually anything for that matter. Animals, on the other hand, were in his mind merely machines.
Although his views were not universally accepted, they became very prominent in Europe and North America.
That was long before Charles Darwin's seminal publication, The Origin of Species, in 1859, where he explained the concept of evolution and natural selection in detail, and in particular also argued for the continuity between humans and other species.
But even long after the theory of evolution by natural selection became widely accepted, humans still had quite a confident self-image. For a long time, we believed us to be the only species to be capable of feats like tool use and language.
In 1960, Jane Goodall, the famous English primatologist, set a new standard for studying animals in the wild by immersing herself into their forest habitat. There, she observed a chimpanzee removing the leaves from a twig and use it to fish for termites.
Because of that, she is usually credited with first documenting tool use in non-human animals. But actually, it's quite possible that people observed such tool use already much earlier. One of Aesop's fables, that was an ancient Greek storyteller, describes a crow dropping pebbles into a pitcher until the water level rises enough for it to drink from it. Modern studies on cognition in birds were able to reproduce exactly this behavior, demonstrating an understanding of water displacement in crows and other birds.
As of today, tool use is documented in many different species, among them the already mentioned birds, great apes, but also other mammals and even squids.
Talking about squids, we do consider them pretty smart, despite them basically being glorified sea slugs. I mean, they are evolutionarily very far from us humans and any other vertebrate, belonging to the same phylum as oysters and snails. Yet they are capable of opening jars, just like we do.
Yeah, I feel like we're actually quite eager to attribute some level of intelligence to animals that are capable of doing similar things as we humans, such as using tools.
But Whether or not an animal uses tools can surely not be the only criterion, right? Maybe some of these behaviors look very impressive, but actually are rather inflexible and can only be applied to a very specific context. And maybe not every smart animal has a use for tools in the first place, right? Is there any way to actually quantify that? Last episode, we talked about IQ tests in humans, which already come with their own problems. Surely there must be a way to test an animal's intelligence as well?
IQ tests are a bit hard to do in most non-human animals, as the Affinity 2 and the Patience 4 questionnaires seems rather unique to our species. But we can test their intelligence, yes. It's just a bit more difficult to do than in humans.
That's right. But there are researchers who are up to the challenge. You just need the right tools and know what to look for.
In today's episode, we will try to shed some light on where and how to find intelligence in the animal kingdom. Can we test for animal intelligence? And how do we do that? Can, or even should, we compare intelligence across different species? Or do different animals maybe display very different forms of intelligence?
We will hear from two scientists who are, among others, investigating these questions. They are working on very different species and are focusing on different aspects of intelligence. But interestingly, they share some conclusions and opinions when it comes to identifying intelligent behavior.
Let's hear about what current research has to say about animal intelligence after a short break. Hi Olga, thanks for joining.
Hi, glad to be here.
You've been talking to some interesting people about animal intelligence, right?
Yep, fascinating stuff and fun too to talk about animals as different as chimps, cockatoos, bonobos, dolphins, crows, and the surprising things they can do.
In our first segment, we already noticed that we are quite eager to call a cockatoo intelligent, but it may be problematic to use this term too liberally. So it seems like whenever we make intuitive judgments about intelligence, we to some extent make a comparison with ourselves, with humans. How do we talk about intelligence in non-human animals, most of which are very different to us, like cockatoos?
Since they are so different to us, different bodies, different needs, different habitats, it becomes very tricky to study their cognitive abilities and to figure out whether they are intelligent in any meaningful sense or not. We also have to avoid our own biases. Non-human animals may be very intelligent, but in a different way, not like humans. So reserving the term intelligence to humans sounds quite premature, not to say unfair.
Right. But if we cannot really talk to them and they're not interested in all these tests that we usually come up with for humans, like IQ tests, chess, or maths, then what are we talking about when we consider the question of whether non-human animals are intelligent or not?
Well, we can consider intelligence in wider terms that will include things that non-human animals might be able to do. And then we can look and see which animals do those things, if they are anyhow well, and so on.
So there's lots of bits of communication where a general concept of intelligence will come in. And there I would think, issues relevant to explaining what might be going on could be spelled out in terms of capacity for making inferences about goals, for entertaining a certain number of things simultaneously in working memory, for having good concentration abilities, and for being able to entertain and respond in flexible ways. It's not a concept of intelligence, but I think it's lots of ways in which that slightly vague concept might be implicated in the things that I care about.
Oh, and that's Richard Moore.
I'm Richard Moore. I'm a Future Leaders Research Fellow at the University of Warwick, and I'm a philosopher who works on issues connected to animal communication and cognitive development.
Yeah, I guess that makes sense. Looking into how well an animal can infer goals, concentrate on a task, and solve it in flexible ways. But still, we cannot just give it any kind of task, right? How do we study animal intelligence then? Where do we even start looking?
Well, a good place to start are our closest relatives, great apes. We do consider ourselves pretty smart, so if we're correct about that, chances are our close relatives are similar to us in this aspect.
So perhaps the thing that I'm most known for is studying similarities and differences between human and great ape communication as a way of gaining insights into the ways in which human language possibly evolved. So if we we can use chimpanzees and bonobos, for example, as a way of modeling what were potentially the communicative abilities of our last common ancestor with them 6 or 7 million years ago. So if there's a behavior in the bonobo and chimpanzee repertoire that overlaps with one of ours, that's a likely indicator it was also present in our last common ancestor 6 million years ago. And so we can use that as a kind of starting point for plotting the way that potential changes might have accrued in evolutionary history, either through biological changes, adaptations, or through cultural changes to achieve the end product of human language.
That's good. Now we have a place to start looking. But what is it that we should be looking for? Are there any certain hallmarks of intelligence?
One thing, as Richard mentioned, is communication. Can animals communicate with each other in complex ways, a bit like we do when we talk to each other or make gestures? Can they have something similar to a language? Another useful clue is using tools. Do some non-human species use tools? If so, how? Do they do it automatically, as if pre-programmed to use, say, rocks to smash shells? Or do they change bits of the environment in some creative ways to build tools that are useful for solving some novel or difficult problems? Tool use in birds is one of the main interests of another scientist I spoke with, Auersperg.
So I'm an assistant professor at the Messerli Institute at the Veterinary University of Vienna. And I'm a cognitive biologist with background in zoology. So I'm interested in how animals think, basically.
By the way, she's the one who carried out the cockatoo experiments, which led to the impressive feat by Muppet, the cockatoo that we heard about earlier.
Cool. But if we want to take tool use as a criterion for intelligence, I guess for some tools you have to be smarter than for others, no?
You're right that not every kind of tool use is good evidence for intelligence. But as Alice explained, it's more complicated than what you said.
Well, there are two types of tool use, very, very basically said. And one, you would say, is the kind of tool use that you would call intelligence. So for instance, imagine you have two animals doing exactly the same thing. That you have, for example, you have this chimpanzee in a zoo, and he figured out at some point, he didn't like the zoo visitors to throw stones at them. And they would run away and he would be very happy. And the zookeepers would try to keep him from throwing stones at them. Then he would invent hiding places to hide his missiles in order to still be able to do this. And then you have an animal like an antlion who's also flicking grains of sand at ants in order to make them fall into the trap. But here, this animal has not invented this behavior. It is not a necessity. It is a necessity to this animal. And for the other animal, it's an opportunity for the chimpanzee. But for the antlion, it is something that has a strong genetic component, at least. And it is an animal that is shown across the whole species. So every antlion has this behavior with a strong genetic component. So you could differentiate between stereotype and flexible tool use. And only the flexible tool use that comes from opportunity and creativity and innovation is the one that is also linked to intelligence.
Right, so there's at least a certain kind of tool use that seems to be a good sign that there is something going on in these animals that may count as intelligence?
Alice calls this sort of intelligence technical intelligence.
Well, my research is interested in one aspect of intelligence. So I'm interested in, if you say technical intelligence, how animals understand their physical environment, whether they understand certain object relationships and can use them and how they can use them. And that tells us something about the evolution of intelligence. If we study complex behavior in animals, we can look at the different, as I said before, the different environments that triggered those behaviors. And then we understand the onset of certain types of intelligence.
So Alice mentioned the evolution of intelligence, but here we are talking about birds, so animals that are very far away from us in the evolutionary tree of life. This makes it all the more impressive, I guess, that this technical intelligence can be found in animals as far apart from each other as humans and cockatoos.
There are also other perks of studying animals very different from us, according to Ellis.
If we study tool use in an animal that is closely related to us, like a chimpanzee, it is likely that our common ancestor with that chimpanzee was probably also a tool user because we're that closely related. And then we don't know what triggered the tool use, the complex behavior, because we don't know what the environment that our most common ancestor lived in was like very much. So it is interesting to study an animal where the same kind of complex behavior evolved completely independently. And birds are very distantly related to us. So there are about 300 million years of evolution between us and the Goffin's cockatoo. But if they also are able to develop similar abilities of thinking, then we can look at what kind of environment do we have in common, what kind of physical environment and what kind of social environment, and what is it that actually triggers these complex cognitive abilities.
So the idea here is that maybe there's a sort of situation that happened in our evolutionary history that created some sort of selection pressure for animals in general to become more intelligent.
Exactly, even though it's tricky, to say the least, to compare intelligence between species.
Well, we can compare performance in certain aspects of intelligence, but we can't, I don't think that you can say that you can map intelligence in saying, okay, this animal is as intelligent as a chimpanzee, and the Goffin is as intelligent as a chimpanzee, and the child is as intelligent, the 4-year-old child is as intelligent as a whatever capuchin monkey. You can't say that because there are so many different types of complex thinking, intelligence, if you will. And you would have to compare them across all of these domains and in all of these tasks. So that isn't really possible. But you can say that in certain areas, some animals seem to have the necessity to invest in intelligence and flexible thinking due to certain reasons more than others. And that is really interesting. And that looking at what these animals face in the natural environment, or when these abilities evolved, tells us something about why these animals evolved this kind of intelligence and whether it had similar reasons as in ourselves.
Interesting. So that actually means that our human ancestors had similar problems to deal with as the ancestors of the cockatoos?
Yes, and there are useful distinctions between different kinds of selection pressure that can lead to the same intelligent outcomes.
There are two main hypotheses for intelligence, and that is that animals are challenged either by their physical environment or by their complex social environment. But there can be many little subsources of that, obviously, but the main sources of intelligence are said to be reasons for it to develop, because it is very costly, from complexities in your social or from your physical environment.
I guess most of the time, though, both the environmental and the social pressures are important, no?
That's right, but it can also be that in some species, only one of these factors was important, or at least much more important than the other.
One of my favorite birds, for example, is the common raven that my colleagues studied them in Vienna, and they are real little politicians. As I said, most corvids are caching food, for example, and the ravens, they go to these carcasses for feeding. That means that they have to get the food as quickly as possible because there are many ravens at the carcasses, and hide it as quickly as possible. But the problem is that other birds are watching you. So you have to keep track on who is watching you, and you also have to know the relationship between you and that other bird in rank. So their social environment is very complex, and they also have these long, very extensive pair bonds where they have to care for another, and they have sibling bonds. So they have a very complex social system, and they show amazing cognitive abilities in the social domain that I don't think our birds could keep up with. So as I said from the very beginning, there are different types of intelligence. And just because an animal is not using tools, it does not at all mean that it has to be stupid. It can be equally intelligent, just the intelligence comes from a different source, maybe not the physical environment, but maybe the social environment, or maybe another aspect of the physical environment.
So these ravens as politicians with their intensive bonds, that almost sounds a bit like human, doesn't it?
Well, it's very appealing to project what we know about ourselves onto them. But we should always be careful with that. Still, there are other interesting things that animals do that look just like what humans do.
What I think is very similar to primates is the way that they interact with objects in general. When you look at them play, you see the sort of play that looks like when you watch a toddler, 2-year-old toddler playing with objects. So they stack objects on top of each other. They stack rings on poles. They insert and stuff object into tiny holes without any food reward, just out of play. They fit shapes. So, for example, they try to fit little cubes through our aviary crit and things like that. They play with objects, combining them in very, very complex way. And I ran a big study across several animals, like several corvids and several parrots. And we found that the play of the goffins is a little bit different of that of other parrots, and that these combinations are very frequent, and also that they don't combine only in one certain way, because, for example, we also tested the New Caledonian crow, which is a specialized tool user, and when they combine playfully, they do mainly inserting things, but they wouldn't do all the other stuff, but the goffins would. And this is also what you would see within primates, in the primates that are also found to be habitual tool users, like the great apes and the capuchin monkeys. So this approach towards objects is very similar to primates.
So maybe a good candidate for a commonality between all or many or maybe most intelligent animals is that they play?
That's cool, isn't it? A thing that we often don't take all that seriously may be one of the keys for developing intelligence in humans, bonobos, cockatoos, and other species.
Right, I can imagine them learning a great deal of their skills by playing around as youngs. I guess in species that don't play much, we also don't see such strong difference between the individuals.
Indeed, let's go back to the example of an antlion. Here, all individuals have similar skills of scent throwing, pretty advanced, and we take this similarity as indication for their behavior to be more hard-coded in their genes. Generally, when there is not much difference between individuals, we are not so happy to call this behavior intelligent.
Does it mean that intelligent animals differ between each other, like humans do?
I would say, depending on the task.
Well, in the cockatoos, I don't think it's very different to humans what we find. We just find that there are extreme differences in some tasks. In some tasks, there aren't any. If the task is easy for them, then you won't find as many differences, obviously. If the task is very difficult, you have some birds that have certain, you could almost say, talents. We have, for example, in our group, we have a couple of birds who are always very good with certain tool use tasks, but not with others. Then we have these 2 females who are not as good in some of the tool use tasks, but in the very, very difficult ones, they're suddenly the only ones who can solve them. So it's quite unpredictable, but sometimes you can tell, for example, you have certain personality features that trigger certain performances. For example, if you have animals that are what we call neophobic, that are more afraid to go towards novel things, they're usually also not as hands-on when you give them complex problems where they have a lot of haptic exploration required in order for them to find a solution easily. And this has an influence. In neophobia, you also find a lot more in lower ranking individuals. So this is a little bit connected. Generally, you also, I would say, you just have talents.
Oh, wow. So they actually do have personalities too.
Well, that's one way of putting it, but we always have to watch our language there.
Talking about language, there is quite some evidence that some non-human animals are really good at communicating, like parrots and perhaps especially some of our cousins, great apes like bonobos and chimpanzees.
That's true, but we have to see in detail how they come to learn and use language. Let's go back to Richard, who has lots to say about this.
What we now know about bonobo and chimpanzee communication is that they have a range of gestures and vocalizations that could reasonably be said to be meaningful. So their gestures have content that might be akin to something like give or come here or chase me or leave me, that sort of thing. But one element that we take to be crucial for human language and that many people think is the defining feature of human language is syntax. So not just meaningful elements, but meaningful elements that can be combined into longer elements in syntactically structured ways. And it looks like that syntactic structure is not present in chimpanzees and bonobos. At least unenculturated chimpanzees and bonobos, so ones that are raised in zoos or that live in the wild, don't in any sophisticated way combine gestures to produce more complex wholes. They do use the gestures that they have quite flexibly, but they tend to use them in isolation or just as a way of repeating the same thing. There's somewhat more evidence that chimpanzees and bonobos raised in human-like environments can combine gestures in more complex ways, but those ways are still less complex than a 2.5, 3-year-old child who is starting to produce sentences. So for example, Kanzi and Panbanisha, enculturated bonobos who have the most fluent communicators using something like human language. And Kanzi might say something like, Kanzi ball, give, or chase, Kanzi, or Kanzi banana. And an interesting thing there is they can comprehend much more than they can produce. So Kanzi has been shown to respond differently to sentences like, put the apple on the bucket and put the bucket on the apple. So he seems to be sensitive to what we think of in terms of syntactic properties. But he also makes quite basic mistakes that 3-year-olds don't make. So for example, if you say to Kanzi, bring me the apple and the book, he only brings one of them. And that seems to be because he can't bind two different semantic elements to the same verb.
Wait, bonobos and chimps cannot really speak, can they? If their way of communicating is much simpler than ours, does it then even make sense to call it a language?
Well, they can make vocalizations, but it's true that they are not able to do the difficult things that we do with our complicated vocal apparatus. They simply can't produce as many different sounds as we do. But that's not the central to language, not even for human language. There are so many human languages that are not based on sound, such as, for example, sign language.
Of course. So do they use gestures to communicate?
That would be one way to go. However, two of the most studied bonobos that Richard was talking about, Kanzi and his sister Panbanisha, were trained in a different way. And in any case, while they can't speak, they do seem to understand pretty well what humans tell them.
Perhaps the key thing we mean by language is vocal communication. And since great apes don't have the right vocal apparatus to use their voices flexibly like we do, we don't look for anything resembling language in the vocal domain, or only in very limited ways. Typically, we look for the gestural communication, and also Kanzi and Panbanisha were trained with what's called lexicograms. And lexicograms are things a bit like Ouija boards. So they have lots and lots of pictures of different types of food, different things. And then when you press the keyboard, it makes the sound. So you press the picture of a banana and the keyboard says banana, banana. And they can communicate with humans using those. But they can also understand spoken language.
That's very impressive.
Definitely. But let's be cautious with these things. It's also very impressive what Kanzi and Panbanisha are unable to do with their keyboards full of symbols.
One of the things that's distinctive of Kanzi and Panbanisha is that they use these keyboards quite fluently, but in quite limited ways compared to human communication. So I read an estimation somewhere that Kanzi might know somewhere between 300 and 1,000 signs, depending on how they're counted, but maybe uses only 35 to 40 of those on a daily basis. And it's true that he doesn't structure those in the way that humans would do. Also, he couldn't using his lexigram, and that's one thing worth remarking, in the sense that it doesn't have terms that correspond to all of the elements of sentences. It just has banana, give, and so as options. So it may be that there's some distortion of his abilities there, but as far as we can tell, there's nothing corresponding to the structure of human language. Also, he's a bit more limited in the range of things that he can produce and understand, certainly compared to a human. I would guess, although this is a bit speculative, that there are a range of pragmatic inferences that he is not capable of making, so that there may be some utterances that require quite flexible interpretation, like metaphors, similes, that sort of thing. I wouldn't expect that Kanzi could do any of that, at least in the same way that we could do. So there are elements of everything that he does that correspond to elements of human language. He can produce and understand meaningful utterances. He can track some elements of syntax. He can make some flexible interpretations depending on depending on context.
So these complicated rules of combinations of symbols, sounds, gestures, and so on that human languages have are missing in other great apes?
Yes, that sounds right. These rules of combinations are what makes the syntax of a language. And, according to our guest, it seems that only humans have complex syntax.
As far as we know, humans are the only species to have syntax in any substantial form. There's lots of ongoing empirical research that attempts to show syntax-like elements in different species. Some of that is quite persuasive, but what they're showing is extremely limited. There are some cases of what might be called combinatorial elements in ape and monkey communication, perhaps where you get certain monkey species that produce two different vocalizations, and then they can combine those two vocalizations to produce a third. There's something corresponding to the extent that the two elements are being combined there. Some people have argued that that corresponds to elements of human syntax. But if it does so in an extremely limited way. And certainly we don't know of any cases where more than two elements are combined, except occasionally in the speech of the gestures of apes like Kanzi and Panbanisha. But there are a couple of things that we have to be careful of here. So one, people working with enculturated great apes have often made very inflated claims about the abilities of those great apes. So for example, I guess you've seen videos of Coco the gorilla, the gorilla who was purported to, it was clearly faked, but giving a speech to the UN about the future of the rainforests or something like that. It's a feature of people who live with, and often, not always, it's a feature of people who spend a great deal of time working with animals like this, that they become a bit less scientific in their interpretation of what's going on. And when you look at the more cautious interpretations of what's going on in these utterances produced by enculturated great apes, they differ very substantially from what different authors have claimed at different times. There's a very good research called Esteban Rivas, who has done some interpretations of the gestures of chimpanzees like Washoe, and said there's much less going on there than others have claimed. That's not to say there's nothing going on. It's still interesting, but it's not the same.
We can say, write, and hopefully understand very long and convoluted sentences with lots of commas, asides, complex verbal tenses, etc., not to mention metaphors and other things like that. So these are abilities that only humans have?
As far as we know, yes, but only as long as we don't take into account differences in performance and competence. As soon as we do take them into account, things become more complicated.
Also, it's the case that researchers making claims about language sometimes disagree about what that entails. So in response to some of the evidence that there are elements of recombination in monkey calls, people in the Chomskyan tradition have reasserted that, well, what makes human communication special is not that there are some elements of recombination, but that there are potentially infinite elements of recombination in what we can do. So in principle, there is no upward limit on the number of words I can combine into a meaningful sentence. What limits it is the human capacity to interpret it and remember what's been said. But Chomskyans make a distinction between what they call performance and competence. And performance is what you can do in practice. It's limited by working memory and attention. And competence is the underlying ability. And the claim about what's unique to humans is that we alone have this unlimited competence for syntax recombination. The issue is a bit more complicated there, though, because there's also a methodological difference in the way that the claims are being tested and made. So, for example, when Chomskyans make claims about human competence being what makes us unique, they're typically comparing human competence with great ape performance and then making assumptions about great ape competence based on their performance. And what their performance suggests is that there are a limited number of things that great apes can do in comparison to humans, but that's potentially not a difference in competence so much as a difference in performance. Sorry, this gets a bit hard to follow up points. One possibility, though, is just that great apes don't have fundamentally different underlying competence for us, but there are much stronger limitations on what they can do with it. So the performance might be different, but the underlying competence the same. I'm not saying that's the case. I'm just saying that when these claims are made, often they're not comparing like with like.
It's also not fully clear what made us, humans, to be able to use and understand complex syntax, all these sophisticated rules of combination of symbols that we see in our languages, while other species, including our close cousins, just don't do this.
But are there some ideas about that?
There are, and especially two are particularly influential, both of which, by the way, connect with things that we discussed with Alice about the evolution of intelligence. One is precisely about tool use.
There are currently lots of theories about why humans might have evolved to use syntax in the way that chimpanzees and bonobos didn't. Some people think it's connected to tool use. So Kim Sterelny and Ron Planer are arguing in a book that, and this is an idea that's been popular in archaeology as well, that just as our sentences are structured, so are lots of our actions. Right? So if you think about crafting a tool, for example, you have to do things in a particular order. Like if you're making a bow and arrow, you shave down the stick to the right length first, and then you curve it, and then you string it, or something like that. And they think that the structure of sentences might just have been inherited from the structure of action. And it's because humans engage in these more complex forms of action than great apes do that we also have that more complex form of thought. Chomsky and Berwick have argued that the structure of sentences might instead have been inherited from planning. And so we underwent some adaptation for at some point for being able to think about the future and plan more. And then maybe that structure might have been exapted for use in natural languages, but we don't really know.
Can you guess the other idea about why we humans developed complex syntax?
Well, from what you said, it must be something with social interactions, right?
Precisely.
Potentially the hierarchical feature of syntax evolved for communication, so not action or not planning, but communication. So Liliana Pragovac, for example, thinks that it was under a selective pressure for more expressive communication that we started to somehow undergo selection for combining elements of sentences, and that the more complex forms of thought followed that. And then you got something like a feedback loop where gradually As the natural languages developed, they led to selection pressure for more complex natural languages, which enabled more complex thoughts, and gradually feedback loop imposed more and more structure on the utterances.
They both sound actually quite plausible, and maybe they're both getting us to a part of the story that makes us humans stand apart from other animals when it comes to language.
Yep, and language is a superior important tool for us. We can send information around, learn from people long dead, use it to organize our thoughts. It's difficult to overstate all the things we are able to do or are able to do better because we have rich, complex languages. It may well be that an important part of what makes us humans so intelligent after all is that we invented this flexible, powerful piece of technology, language.
Right. As skillful as many animals are in solving problems and using tools, as far as we know today, this particular tool, language, seems to be something that other animals seem not to be able to master. I really enjoyed this, Olga. Thanks a lot.
My pleasure. See you soon.
So, Benny, considering what we just learned, what do you think? Is Bob the Sponge intelligent?
I wouldn't say so. I mean, for a creature without a brain or any neurons, avoiding a predator surely is already quite impressive. However, at least to my knowledge, they are not really capable of any learning or any plasticity in their behavior. And I would say that required to call it intelligent. And I mean, even some plants, like, for instance, the Venus flytrap, will desensitize to repeated stimuli and then not close anymore. So even plants can display some flexibility.
Yeah, I'm not sure if I would actually call that learning, but I'll give you that it is pretty amazing what plants can do. And while this is maybe not really behavior in the classical sense, and they rather grow in a way, but some people claim that they also do display some sort of intelligence.
Which is at least controversial.
Absolutely. And we'll also dedicate a whole episode on this question. Where should we draw the line, or like a boundary of what we could still call intelligence?
Yeah, maybe as a good rule of thumb, if it can't integrate new information and modify its behavior accordingly, it's probably not that intelligent.
That is a good start, I would say. But again, looking back to our interviews, do you think that we identified other hallmarks of intelligence?
Yeah, I would say at least tool use certainly qualifies as a hallmark of intelligence to some extent. At least the kind that is adaptive and learned. So I would say that any animal that you can teach to use a new tool certainly is somewhat intelligent. It probably is not every form of tool use, like Alice said, those ant lions that flick sand at ants. I'm not sure if you can call that intelligent if all the antlions are born with that skill and it's nothing really that they really learn, but something that is inherent to the species.
Yeah, but I guess in general with insects, there is this idea not only about the antlion, but in general that they only have inherent behavior. So they only follow very simple rules and are basically born with that. And if they show intelligent behavior, they can only do that in very large numbers, like in swarms or hives.
Yeah, I mean, that's what we call swarm intelligence. I think we even have a whole episode dedicated to that.
We certainly do. But even individually, some insects show really remarkable capabilities. So, for example, the bumblebee. It can be taught to push a ball into a dedicated hole by just receiving some sugar water reward.
Yeah, I mean, that seems like that's definitely learning behavior. That's more than I would have expected from a bug.
Right, but now the really cool part about this is that not only by receiving that sugar reward itself, but even just by watching how another bumblebee gets a reward, it can learn that it has to push this ball. So it really learns from these social interactions.
That's even more impressive. I mean, we are also doing some research on social learning in mice here at Science of Intelligence. And I know from our own experience that it's not always trivial to communicate to the mice that it's expected to learn from their conspecific behavior. I think generally when designing experiments to test an animal's cognitive abilities, you need to keep in mind what exactly you are testing and how you present it to the animal.
Right. I think there are multiple pretty famous examples for intelligence testing gone wrong. One of them is Clever Hans. That was a famous horse at the time, around the beginning of the 20th century. where his owner claimed that Hans could perform arithmetics and other really impressive tasks. So, for example, when the owner asked Hans, "What is 18 divided by 6?" then Hans tapped with his hoof 3 times on the floor. And that did not only convince the audience, but also really large parts of the scientific community at the time. Before then, psychologist Oskar Pfungst showed that the horse could only give the right answers when the trainer knew them. So Hans was not actually doing these arithmetics in his head, but it was basically just observing how the trainer reacted. And as soon as the trainer was happy with the answer, he just stopped tapping on the floor.
I mean, that still sounds like a pretty smart horse to me, while not in quite the way that they initially claimed. As I said, when you want to test intelligence in non-human animals, you need to keep in mind what exactly you want to test, how you communicate that, and also what species you want to test and what specific requirements that poses to your design.
Right. The other potential hallmark that we talked about in the interviews is communication. But our conclusion there was that it is at least a bit tricky in the context of animal intelligence. At least as far as we know today, humans really stick out when it comes to having rich and complex language.
Yeah, that's right. However, we should say that after we interviewed Richard, there was a new study that came out that actually found that crows are capable of recursive reasoning.
What does recursive?
Basically, they managed to teach them a sequence of symbols, and from that, the crows were able to actually expand their knowledge to new symbols that were not presented to them anymore, and also put them in logical order. So basically, from something they were taught, they were able to expand the logic to something new. And actually, that was for a long time thought to be unique to humans and is actually crucial to grammar and human language. And yeah, it seems that not only we can do it, but also corvids.
Yeah, funny. So I think in general, as soon as we try to define these bright lines like man as the tool user, or in this case now, man as the only animal that can use proper grammar, whenever we try to do that, these lines are continuously being pushed by new research coming in.
Yeah, and I mean, not even only by what we find in other species. I mean, already today we can build machines and AIs that surpass us in certain tasks like complex language generation, math, or games like chess.
Right, and these are the things that we are, as humans, typically very proud of, right? So maybe these are kind of the things that we think distinguish us from maybe other animals, but now we have computers that are actually much better in doing that. And yeah, I think it is really impressive what current artificial intelligence can do, but it's also equally interesting to look into the things where even the smartest computer programs and robots today still struggle. And actually, these are very often the things that, from a human or also an animal perspective, they seem to be quite easy or effortless tasks, like recognizing that your kin needs help, or like opening doors, or also using tools, things that we talked about in the animal context. But we will talk about what AI can do and also where it still fails in the next episode.
So see you next time in Punching Cards, the podcast about all things intelligent.
And now, time for some fun facts. Richard talked a lot about the quite impressive linguistic ability of Kanzi, the bonobo. But there's something else about Kanzi that's really interesting. His language training was somewhat accidental, because researchers were actually training his adoptive mother, Matata, to use the keyboard of symbols or lexicograms. And Kanzi was just there that day by pure chance. To everyone's surprise, though, in a moment in which Matata wasn't around, Kanzi started using the keyboard by himself, and, as it turned out, was quite good at it. Punching Cards, the podcast about all things intelligent, is a production of the Science of Intelligence Cluster in Berlin, part of the Excellence Initiative of the German Research Foundation. The podcast is produced, scripted, and coordinated by Aravind Battaje, Dimitri Coelho Mollo, Benjamin Lang, Nicolas Roth, Olga Shurygina, and Solveig Steinhardt. Editing by Valeria Becattini. The music was composed and performed by Solveig Steinhardt and Dimitri Coelho Mollo, and mixed and produced by Aravind Battaje. You can find and follow our podcast on Spotify and Apple Music and all your favorite podcast platforms. For show notes, links to additional material, more information, and to contact us, visit www.scienceofintelligence.de/punchingcards or follow Science of Intelligence on Twitter.